types of reactions. Now, when you're talking about these types of reactions, we need to understand acid base reactions, and we also need to understand precipitation reactions, and then we are going to be able to understand redox reactions. Now, just a brief on acid base reactions. So, we say an acid is a proton donor. Anything that donates a proton is called an acid. So an acid is a proton donor. Now when you're talking about a proton, in chemistry a proton is simply an hydrogen ion. And then a base is a proton acceptor. So this one is going to be accepting a proton. The acid is going to be donating a proton. So basically when we're talking about acids, acids are compounds which have got an hydrogen in them. That is why acids have got a sour taste, because of the presence of hydrogen ion. And then bases are mostly metal oxides or metal hydroxides. So for example, acids you can talk of hydrochloric acid. You can see we have got an H here. So we have got acids in the form HX. These are called monoprotic acids. So this protic is just meaning a proton, and we know that's an hydrogen. So meaning they've got only one hydrogen. And then we have got diprotic acid in this form. We have got also polyprotic acids with more than two hydrogens. This is going to be called a polyprotic acid. An example of a monoprotic acid that we can give is hydrochloric acid, and also this one. Oh, this is a fluorine. When you're talking about diprotic acid, we can give sulfuric acid, which is like that. If we are talking of polyprotic acids with three hydrogens, you can think of this one, which is phosphoric acid. So these are some examples. When we are talking about bases, you can think of sodium hydroxide. These are just metal hydroxides. Potassium hydroxide, magnesium hydroxide. You also have, we can talk of also ammonia. Ammonia, I think, is one of the few which are not hydroxides, but it's a base. So whenever an acid reacts with a base, what you are going to form is water and a salt. So this chemical reaction is going to give you a salt and water. So for example, you can give hydrochloric acid reacting with sodium hydroxide. What are we going to get? So in here, the hydrogen and the chlorine are the two compounds which you have. One of them is positive, the other one is negative. So what is going to happen is the hydrogen is positive, the chlorine is negative. Here sodium is a metal. Sodium is what? Is positive. The hydroxide is negative. The positive one here is going to react with the negative one there, and then also these ones. Now when you're writing a formula for something, always start with the positive one. So we're going to start with the sodium and then the chlorine. So that is going to be sodium chloride. And then this hydrogen reacts with this hydroxide. That is going to form water. So you need to also write the state symbols. Hydrochloric acid is in aqueous. When you put liquid here, then that's no longer, I mean, if you put gas, it's no longer hydrochloric acid, but hydrogen chloride is a gas. Sodium hydroxide is also in aqueous, meaning it dissolves in water. You have got sodium chloride. This is table salt, the salt we use. This is also dissolves in water, so it's in aqueous, and then water is a liquid. Now from here you can write or you can deduce an ionic equation. So to deduce the ionic equation here, you're going to break the atoms which are present into ions. So first these are going to be broken into ions. So we're going to have hydrogen plus, and then you have got a chlorine minus. So just this one has broken down into its ions. and then plus you have got a sodium hydroxide. So only those which are in aqueous are going to break into ions. Liquids and solids don't break into ions. And then the sodium is going to also break into ions, and then the hydroxide alone like that. And this is going to give you the sodium chloride. The sodium is also going to break into ions. The chlorine is also going to break into ions like that. But water is a liquid, it will not. So it will still remain like that. And then you're going to look on the left and on the right. The ions which are the same should cancel them. See chlorine here, sodium here, sodium here. So these ions which gets cancelled in an ionic equation, they're called spectator ions. So we have got H plus which has remained, and this is going to be in aqueous. And then you have got the OH which has remained. This is also in aqueous. And this is going to form H2O. That's the only thing that has remained on the product side, which is a liquid. So this reaction we can see here down is called the net ionic equation. So you can see the net ionic equation, as long as you balance this reaction which is here, it is also going to be balanced just itself. So this is the reaction that gets to happen to form water. Okay, we'll give another example. So we can think of, we're going to get an acid, sulfuric acid. We can react it with any base, let's say potassium hydroxide. This is in aqueous, also this is in aqueous. So what are you going to form? The hydrogen interacts with a hydroxide to form water. The potassium is going to interact with a sulfate. So we're going to have potassium sulfate. By now we should be able to know, and we guess you already know from high school, that sulfate is a radical. It has got a valence of 2. Potassium has got a valence of 1. So the 1 on the potassium is going to go on the sulfate, and then the valence 2 from the sulfate is going to come on the potassium like that. And this also is soluble. And you are going to have water as a product. So this is a salt. You have got water there, which is a liquid. Is this reaction balanced? Look at the potassium. Here we have got 2, here we only have 1. So we're going to put a 2 in front here. The hydroxides, we have 2 here. What of the other side? Now we're going to count each atom. So I've got 2 hydrogens and then 2 hydrogens here. You can see these 2 applies to everything, meaning we have got 4 hydrogens. If we come this side, we only have 2 hydrogens. So we're going to put also a 2 in front here. Let's go to the oxygens. So we've got 4 plus 2, that gives us 6. And then here I've got 4 plus 2, that gives us also 6. So the reaction is now balanced. We can now deduce the ionic equation. So those which are in aqueous solution are going to disassociate into ions. These 2 which you can see down here. So here we've got a sulfate and the hydrogen. So the 2 that you can see down, the hydrogen, is going to come in front like that, and then you're going to have hydrogen plus. That's the charge for hydrogen in this reaction. And then you have got a sulfate, SO4. Now a sulfate has got a charge of -2. And then you have got these 2 in front. You've got potassium. Potassium is a metal, it has got a charge of +1. This 2 is also applying to the hydroxide, and the hydroxide has a charge of -1. And then on the product you have got 2 potassiums. So this is going to be 2. The potassium has got a charge of +1, it is in group 1. And then you have got a sulfate which has got a charge of 2 minus. Water will not disassociate because it's a liquid. And then what is appearing in both sides of the reaction cancels. We've got 2 hydrogen ions. No, the hydrogens will not cancel. The sulfate here will cancel with the sulfate, and then the potassium is also going to cancel the potassium. So what you are going to see is 2 hydrogen ions being able to react with 2 hydroxide ions, and this is going to give you 2 water molecules. This is a liquid, this is in aqueous, this is also in aqueous. So you can count. You've got 2 hydrogens plus these 2, that is going to give you 4. And then you have got also 4 here, the hydrogen, so that is balanced. And then if you look at the oxygens, you've got 2 here also to this side. So it is a balanced net ionic equation. So these are acid-base reactions. Now at times an acid can react with a metal. What happens? So when an acid reacts with a metal, what you are going to form is a salt and hydrogen molecule. For example, you can say hydrochloric acid reacts with a metal, let's say magnesium. What you are going to have in this reaction is magnesium chloride. Magnesium has got a valence of 2, chlorine has got a valence of 1. So the 2 from the magnesium is going to come here. And then you are going to form hydrogen molecule. These atoms, hydrogen always exists with a 2 down. Chlorine, salt, nitrogen, oxygen, fluorine. So whenever you are writing a formula for hydrogen alone, it should always contain a 2 down. These exist as a diatomic gas. So is the reaction balanced? You can see 2 hydrogens here, so we need to put a 2 here. And then the chlorines are also balanced with a 2 here. The magnesium is just alone. So this is what happens. A metal reacting with an acid, always a salt and an hydrogen molecule, a hydrogen molecule. Now again, you can have an acid reacting with a carbonate, metal carbonate. And this reaction is always going to produce a salt, water, and carbon dioxide. You can think of, let's say, sulfuric acid reacting with any carbonate, let's say calcium carbonate. This is going to give you the salt, that is going to give you the calcium is going to interact with the sulfate, that is going to give you calcium sulfate. That's a symbol because calcium has a valence of 2, sulfate also a valence of 2. And then you're also going to have water and carbon dioxide. This you just need to know, because if you want to see how atoms are going to react, you might not be able to see. Is this reaction balanced? You've got 2 hydrogens, 2 hydrogens. You've got 1 sulfur, 1 sulfur. Oxygen, there are 4 here plus 3, 7. 4 here plus 1 plus 2, 7. So everything is balanced. So that is how you get just everything. You can also have, let's say you are reacting, let's say phosphoric acid or carbonic acid. Let me use phosphoric acid. You are reacting it with potassium carbonate. Potassium carbonate is like that because potassium is having a valence of 1 and the carbonate a valence of 2. So that's how the formula gets to look. When this reacts, the potassium interacts with the phosphate, forming potassium phosphate. Potassium has got a valence of 3. That 3 is going to come here. Phosphate has got a valence of 3, which comes down. Potassium has got a valence of 1, which is going to come here. But 1 doesn't affect anything. And then you're going to have water and also carbon dioxide. The reaction, you can see, is not balanced. We have got 2 potassium and then 3 this side. So we need to balance that. We're going to swap these numbers. We're going to put a 3 here and a 2 here. When we do that, we can see that we've made, let's look at first the potassium. We have got now 2 potassium atoms here, so we need to put also a 2 here to balance it. If we put a 2 here, we see we've got 6 hydrogens, so meaning we also need to have 6 hydrogen. We're going to put a 3 there. If we do that, let's count the oxygens. We have got 8 plus 9. Okay, if we multiply this 3 times this 3, that's going to give us 9. So I've got 8 plus 9, which is 17. So this side we're going to have 8 plus a 3 here. That is going to give us 12. And then we have got 2 here. That's not balanced. And if we can see, this 3 has made to have 3 carbons here. That means we need to have 3 carbons this side. So we need to put a 3 there. Let's count. This is going to give us 6 plus this, that's a 9. And then plus this, which is 8. So 9 plus 8, that is also 17. Now the chemical reaction is balanced. So that's how we get to balance also these. So we've looked at what? we've looked at acid-base reactions. These are acid-base reactions, acid-metal reactions, and acid-carbonate reactions. Now, from here, we also need to understand precipitation reactions. A precipitation reaction is a reaction that forms a precipitate. A precipitate is simply a solid. Yes, please go on, Joyce. Yes, Temba. Okay, so you should speak when you can.
What's the symbol for potassium phosphate?
Okay, that's in aqueous. Okay, so now when you are looking at
Okay.
precipitation reactions, you need to know the rules that apply. Okay, so we should be able to know the rules that apply when you're talking about precipitation reactions. And the first ones we should be able to know whenever you're talking about sulfates. When you're talking about sulfates, we've got what we call, can take them as Kabale sulfates, like this. These are insoluble, they don't dissolve. So here this Ca is representing calcium, this one is representing barium, and then this is representing lead. So every time that you have got calcium sulfate, or barium sulfate, or lead sulfate, these are always going to have a state symbol solid. They don't dissolve. They don't dissolve. Now, when you're talking about precipitation reaction, you're going to react two salts. Okay, you're going to react two salts. So we're going to have salt plus salt, and these two salts we are reacting dissolve. So this is a soluble salt reacted with another soluble salt, and then what we are going to form is an insoluble salt and a soluble salt. So this is the reaction that we are going to see. For example, you can talk of let's say I've got potassium sulfate, and this is reacted with barium chloride. These are in aqueous, they dissolve, they are soluble. So what you are going to see is the barium is going to interact with the sulfate. That is going to give you barium sulfate. This is a solid. And then the potassium is going to interact with the chlorine. That is going to give you potassium chloride. This is going to be in aqueous. So a salt plus a salt, giving you a salt and a salt. But one salt of the on the product side is going to be able to dissolve. Is that okay? Is that good? All right. So apart from the sulfates, we have got also chlorides. So we have got what we call selenium chlorides. Selenium chlorides also, they are insoluble. So when you have got this is silver. So when you have got silver the symbol is Ag. Even here, though I've written Si, that's just a way to know it for you to master. Silver chloride, the state symbol is going to be solid. And then lead chloride, the state symbol is also going to be solid. You also have mercury. Mercury, the symbol is Hg. Mercury chloride, the symbol is also solid. So we also need to know this. Carbonyl sulfates, selenium chlorides. And then the others, when you're talking about nitrates, all nitrates are soluble. So when you're talking of, for example, calcium nitrate, potassium nitrate, these compounds get to dissolve in water. Actually, nitrate has got a charge of 1. So it is going to be potassium nitrate like this. So hope we get that. Nitrates dissolve in water. And then alkali metals and ammonium compounds are soluble. So when you see an ammonium compound, this one, NH4 minus, this dissolves in water. And alkaline metals, these metals which are in group 1, they also dissolve. Like potassium, phosphorus, these get to dissolve. Okay. So every time that you've got a potassium reacted with something, you are going to put a solid there. A group 1 element, you are going to put, you're going to put aqueous because they dissolve every time you've got those. And then most hydroxides are insoluble. If you see, most of the hydroxides get to be insoluble in in water, but not all of them. So there are a lot of exceptions. For example, when you talk about hydroxide of group 1 elements, because we are saying group 1 elements dissolve, so if I say potassium hydroxide, this will not be a solid, it is going to be aqueous, because group 1 elements or alkali metals, they always dissolve. It might not be the same with barium hydroxide. This you are going to see a solid there. So let's take note of that. So because of this which is happening here, that is what leads to some properties, some are not dissolving. So you need to know these solubility rules. That's why when a chemical reaction happens, how do you determine which state symbol you're going to use, whether it's aqueous or solid? So these are the rules that you get to follow when you are writing state symbols. Is that good? So it is from here now that we are going to understand redox reactions. And that one we're going to go over it in the on the next one.